The last type of matrix that we're going to apply spectral theory to is positive and negative definite matrices. So let's define these first and then see how these matrices behave when you consider eigenvalues, eigenvectors, things like this. So first, let's give a definition here. We'll still be in the context of A being an n by n symmetric matrix. And remember, this means that A is equal to its transpose, right? And let's say A has eigenvalues lambda 1 through lambda n. These are eigenvalues of A. Then we say A is positive definite if lambda I is greater than or equal to 0 for all I ranging from 1 to n, right? So what we're saying here is you just have strictly positive eigenvalues. Not that they have to be distinct per se, right? There's no reason to assume lambda I couldn't be equal to lambda j for some pair ij in general, but we do require that they're positive. If you can believe it, we define a negative definite matrix let's just say B is negative definite if, let's say it has eigenvalues mu1 through mu n, eigenvalues such that mu I is less than 0 for all I from 1 to n, right? Very simple definitions, intuitive, not much beyond the definition itself, but that doesn't mean there's not a lot that we can learn about the theory. First, let's state a lemma that determines when or a relationship between positive definite and negative definite. So A is, and I think I'm going to save some time here. And for positive definite, I'll just write plus def. So A is positive definite if and only if negative A is negative definite, right? So very intuitive. We won't prove this, but we will use this to prove a stronger theorem. We'll prove the following theorem. So let's let, the same hypotheses. So A is going to be an n by n symmetric matrix. A is positive definite if and only if for every non-zero vector x in Rn, so non-zero means this is an element of Rn without the origin, right? Remember the backslash is the set minus. So this is n-dimensional Euclidean space except the origin, right? So it's like you punctured the origin out. If we have that for every non-zero vector x, we have that x transpose AX is positive. So let's prove this. Before we prove the forward and backward direction of the if and only if, let's first see how we can understand this product here, right? Well, we can understand this product a little more explicitly by using the properties of A to our advantage, right? So since A is symmetric, and we're assuming that in both directions, right? That's not just the hypothesis of the forward implication. Since A is always symmetric, we remember last time when we were looking at orthogonal diagonalization, this means there exists an orthogonal matrix U such that A is orthogonally diagonalizable, right? Which means it's U transpose AU is equal to some diagonal matrix D. And if you'll remember, this is equal to lambda 1 through lambda n along the diagonal. To save myself some time, if you haven't seen this notation, we can write this as diagonal of lambda I here. And this just means down the diagonal, we have the lambda, the eigenvalues, and then everywhere else is 0, right? So let's use this to our advantage when understanding the product X transpose A X here, right? So X transpose A X, well, since A is orthogonally diagonalizable, that means we can write A as X transpose, and then we'll have U, D, U transpose, and then X, right? What we're doing is we're just taking this relationship, but we are isolating A, right? Just take a couple transpose products there. Now we can use associativity to group. So we have X transpose times the orthogonal matrix U, D, and then we have U transpose times the vector X. Now let's define this product here to be, let's just call it Y. So we're going to define Y as X transpose U. Excuse me, let's define that to be Y transpose for the sake of convenience. So let's say Y is this over here. So this is going to be Y transpose D Y, like this. So Y is U transpose X. And you can see if you take the transpose of Y, you get X transpose U, which is this. Now, what does this mean? We have Y transpose, which is Y1, we'll say Y1 through Yn. We have D, which is the diagonal of the lambda i's. And then we have the transpose of, or if Y transpose is a row vector, then Y would be a column vector. So then we'll have, Y1 through Yn like this. Well, what is this product? If you take the product of, right, you would take this product first because you always work right to left. So this would be Y1, blah, 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 through Yn times the column vector lambda 1, Y1, et cetera, lambda n, Yn. We take the next product, you can see what we'll get is lambda 1, Y1 squared plus blah, 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 plus lambda n, Yn squared. Okay, so why did we do this? Well, now we have a much more explicit understanding of this product. And if we're trying to prove or use as a hypothesis that this is positive, we need to know or have a better understanding of what that actually means, right? And hopefully we have a better understanding of that when we can write it out explicitly in terms of coordinates of some vector and our eigenvalues of the original matrix. Now, let's prove this statement. It's an if and only if statement, so we have to prove both directions, right? So let's prove the forward direction. The forward direction means we get to assume that A is positive definite. But what does it mean that A is positive definite? That implies that lambda I is greater than 0 for all I, right, from 1 to n. Now, what else do we know? Well, let's look at, because what we're trying to do is we're trying to prove that this sum up here is greater than 0. Well, to do that, we need to show that each term is greater than or equal to 0, or that they're not all 0, right? So we know that lambda I is greater than or equal to 0. And we also know, right, if you look up here, the other factors of these products are squares, right? So as long as if there exists some j such that yj is not 0, then we would guarantee that X transpose AX is greater than 0, right? Why is that the case? Well, the square of any real number is always positive. The only way it would not be positive is if they were all 0, right? So how do we guarantee that there exists at least one non-zero eigenvalue? The reason that we know there's at least one non-zero eigenvalue is So this existence holds since U transpose is invertible, right? And you're taking the product of an invertible matrix with a non-zero vector, you're going to get at least one entry being non-zero, right? Okay, and if that's the case, then we have that this sum, I'll just write it up here. This is greater than or equal to 0, which we know this was equal to X transpose A X. So we've proven the forward implication. Let's prove the reverse direction, the converse of the statement we've just proven. And to do that, we assume what we were trying to prove in the previous direction, right? Now we want to assume that X transpose A X, which we've learned is equal to lambda 1 y1 squared plus blah, 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 plus lambda n yn squared. We're now assuming that this sum is positive. Well, how do we show now, right? To show that A is positive definite, it suffices to show that every eigenvalue is non-negative, or not non-negative, strictly positive, right? We have that this is true for all X in Rn without the 0 vector, right? If that's true for all of them, we have the freedom to choose any representation of the vector X. And let's be clever and let's choose X to be the vector that is the result of the product U times EJ, where remember EJ is the basis, the standard basis vector that's 0 in every component and then 1 in the jth component, right? So that's the jth spot. Okay. Well, then we know what X is, but remember X played a role in the definition of these components y1 through yn, right? So we need to understand what this does to the vector y. Well, we know y was defined to be U transpose X, which we've chosen X conveniently. So y becomes U transpose times X, which is UEJ, which means, sorry, this is for a given component yi, right? So what we get, we know that for an orthogonal matrix, its transpose is equal to its inverse, right? So this product here, by associativity, we just get that this is the standard basis vector E sub j, which means yi, or the entries of y, this is equal to the vector delta ij, right? Because you're choosing the definition of X based on your index. And so you'll have to choose that for each index, right? And so basically what we get is that for a given sum, you know, you would have lambda 1 y1 squared plus blah, 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 plus lambda n yn squared. Well, the way we've defined these components, this is going to just be equal to lambda j, right? Because when I is equal to j, you'll get 1. Everywhere else, you'll get 0. And so the only term that survives is this lambda j. But we know then that this sum was also equal to X transpose AX, which we had assumed to be positive. And so that means if you do this for every index, j from 1 to n, you get that that eigenvalue is positive, which implies that A is positive definite. Okay, so that gives us, that completes the proof of this theorem. We're going to wrap up our discussion of positive definite matrices, and actually this will wrap up the material over spectral theory. We're going to wrap this up with looking at submatrices. So let's give a definition. A is going to be an n by n matrix with entries, you know, A11 through, and somewhere between 1 and n, we have let's say A1K. So we're looking at some number K, some integer K between 1 and n, right? And then we would have A1n, AN. Down the first column vector, we would have AK1 somewhere, right? AN1, et cetera. And then along the diagonal somewhere, we would have AKK. Okay. We define a submatrix for some K. We say AK, which is equal to A11 through A1K, AK1, blah, 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 AKK. We say this is the K submatrix of A, right? And so basically what you're doing is you're taking a K by K square matrix that starts in the top left entry, and then you cut everything else off, right? So the K plus 1 rows and columns all the way through the nth rows and columns, you just remove those, right? How do these relate to positive definite matrices? So we have a lemma here. And sometimes, you know, if a matrix is like huge, say you have like a 3,000 by 3,000 square matrix or something, well, then it would be really convenient if you could extract information with only having to look at some smaller dimensional matrix, right? And that's kind of why we care about submatrices. But anyway, in relationship to positive definite matrices, we know that A is positive definite. It implies that every submatrix is positive definite. And this is for all K between 1 and n, with our assumption that A is positive definite, right? If you'll remember, A positive definite implies that for every non-zero vector X here, we have that X transpose AX is positive. Well, we can understand a submatrix by considering AK, right? You could think about this as an n by n matrix where you have your AK in the top left corner, and then you have zeros everywhere else. That's an n by n matrix, right? Even though the only entries that are non-zero are in the K by K square matrix there. So because of that, we can write this product here as X transpose 0, right? So you have like your K components, and then the rest are 0 times A times X 0, right? And then you can see by the product, this is 0, which gives us the implication. All right, the last thing I want to do is state a theorem and a corollary relating submatrices to definite matrices. A is positive definite if and only if the determinant of every submatrix is positive. So positive definite matrices are those such that every submatrix has a positive determinant. And again, this is for all K from 1 to n. Because of this theorem, we can state the following corollary. We have that A is negative definite if and only if -1 to the K times the determinant of AK is positive for all K from 1 to n. So this gives us a nice classification of positive and negative definite matrices in terms of the determinant, right? And since the determinant is one of the easier things to not only understand, but to also compute, it's very nice to relate more complicated notions to notions that we understand much more intuitively. Okay, so I think this wraps up spectral theory for the course, and for tomorrow and the remaining 3 lectures next week, we'll take a look at a much more abstract setting. It's a subset of abstract algebra, and we'll look at the notion of vector spaces. We've seen an example of vector spaces already because we've been looking at n-dimensional Euclidean space, right? Obviously, there's a lot going on with vectors, vector addition, multiplication, et cetera, but now we're going to take a much more general approach, a much more abstract approach, and see what vector spaces are in general and not just a geometric setting of n-dimensional Euclidean space.